Okay, hello everyone. Thank you for coming to the class. So this will be we are going to start our chapter 4 actually. So I would like to start with this. It seems like a physics problem. Okay. So I think have you learned this in physics? More or less, right? Okay, so we have x, which we define as a function of distance or position, as t cubed minus 60 squared plus 90. And we are going to observe from t equals 0 to t equals 5. So between this interval, between 0 to 5, we are going to find this average velocity, average speed. Do you know what's the difference? The difference? Okay. You wake up in the early morning. So velocity and speed. Okay. So velocity is we have the difference in distance and then divide by the time. Right? Speed, the distance we travel. Okay. The distance we travel. I don't think that's important in our class, but that's in physics. But let me just write that for you and how it looks like if we solve this. So velocity, okay, this is going to be change in position divided by time or time interval. Okay, time interval. And average speed is the total distance traveled divided by time interval. Okay, so for the first one, finding the velocity, let me write here, average velocity, or let me write as v, like that. This will be s5 minus s0 divided by 5. Okay. So based on our equation, then we can just take 5 and 0 inside the function. And we are going to see that 5 cubed, 125, and then 25, 6 is what? 150. 150 and 125 should be negative 25 and 45 and 25, right? So 25 and 5 will be 20, right? So 20 divided by 5 is 4. Let's say this is going to be in meter and second. So this will be 6 in second. This will be in meter. So we are going to have 4 meter per second. Now, how about the average speed? Because we need to know the total distance. Divided by time. So let's say we are going to have some line number. This is at t equals 0. Let's say so at s0. At s0, it's 0, right? It's 0, so start with 0. So s also 0. At t equal 1, what will happen? 1 minus 6 minus 5 plus 9. So it's 4 meter, right? 4 meter. So maybe here is t equal 1, s equal 4. So we move. So let's say if this is going to be a person, and then he move, this is move to the right, plus 4 meter, right? And then maybe checking t equal to. What will happen t equal to? So S0 is 0, S1 is 4. What happened with the S2? S2 will be what? 8, 4, 6, 24, right? Plus 18. So it will be 2, right? Will be 2. So what should we write here? Remember, x is a position. So 0, this is 0, this is 4. So if this is a position, this is a distance. So 0, maybe 2 is middle, right? Okay. So this will be at t equal to, s equal to. So what's really happened is he moves 4 meters and then he moves back 2 meters here. Okay. So, and I think you already learned also in physics that to solve this, we might want to derive this. Right? And then from x we have s dt, which means that the definition of the velocity function. So we can take the, let me write here. So t cubed minus 6t squared plus 9t. You can take this. Let me write s. So take this with respect to t. So we have the s dt is 3t squared minus 12t plus 9. Or we can say that if we imagine this is a graph, the first derivative, as also we mentioned in previous chapters, this will be our slope, okay? Our slope, right? Our slope. And when the slope is 0, it means the horizontal slope. That will be the one that we are probably looking for, okay? So let me write here. So at ds dt equals 0, we have horizontal slope. Okay. Why this becomes important? Why this equals 0 becomes important? Because the way we have the horizontal slope, like that, we can know from the previous section of that point, if the point is like this, then it will, maybe it is positive and then 0 and then negative, or it is negative and then 0 and then positive. So we can know whether this point are in the lowest point or in the highest point. That's one important point on this 0. So this part here we can solve taking into 0 and then divide all by 3. We have t squared minus 4t plus 3 equals 0. So we get the solution. We take factors for both of for this equation, and we have both possibility. So t is 1 and 3, as we can see from what we have in our illustration. We have 0 and then 1, and then suddenly we go back, which means it's go up and then go down as we travel, like, okay, and then we turn up. Okay. So this we can also say as this point, t equal 1 and t equal 3, we call this is a turning point. So we may have something like that, okay? And all the slope here is positive, right? Positive slope. And then at the top, we have the slope is 0, and then it's going down, negative slope like that. Okay, so we call this point here as a turning point or extreme point. Or sometimes we call also stationary. Okay. And then we can decide whether we have a local max like this one or local min. It depends how we change from positive to negative to say it's local max. From negative to positive, it's local min. Okay. Okay, so back to the questions, the total distance. Okay, so we have 4 and then 2, but maybe this t equal 2 is not really significant. The significant one is this equal 1 and equal 3 because this is the turning point. So let's check S3. Okay, so check S3. Check S3. Let me put this going there. Okay, so S3 is equal. So 3 cubed is 27. 27, 9, 6, 54. 54, 27, negative 27, plus 27, it's 0, right? 0, right? It's 0. Which means it goes all the way back to the starting point. Okay, so 4 meter and then 4 meter again. So he already traveled 8 meter, right? So this is also T3 as is 0. So first is 4 meter, and then second is also moving back to the position 4 meter, so minus 4 meter. But here, this 4 we need to plus them because he moved that long distance. 4, 4. So maybe I will write not positive and negative. Maybe it will confuse you and you will, 4 minus 4, it will be 0. But the meaning here is the total distance he's traveled, okay? So 4, 4, and then maybe we take the S5, which is the 20, right? This one, 20. So 20. So 20, let's say 20 is going to be here. So this is T5, S is 20. And then at the end, he moves back to the right until S equal 20. So this is 20 meter. So the total distance, 4 plus 4 plus 20. Okay. So 8 plus 20, 28. So that's the total distance. So this will be 28 over 5. 5, 6, right? So at this t equal 3, we have also turning point, right? So from left and then go back to the right. So if we try to make sense what happened is actually first we go positive, right? We go positive. So this is t0 and then this is t1. Okay, so we go positive. And then somehow from t1 we go back, which means we go back to the 0. And then after we go back, we move, and then suddenly at t equal 3, we go back again to the right, right? And then this is what this looks like. So we go up, and then turning point, go down, turning point, and go up. And it can be shown as we move ourselves. So we go, and then we go back, and then we go 20 meters. Okay, so 4, 4, and then 20. Okay. Now this illustration might help you to understand what we are going to do next, okay? Which we are going to describe the max and minimum value, okay? And how to apply calculus for sketching a graph. So our goal in this chapter, chapter 4, is actually how to sketch a graph. Like we have a functions, and using some techniques in calculus, without using any additional like software or website to graph, we are able to graph those functions. For example, we are able to tell when the function has the maximum minimum value. We can tell that, right? From this, you can tell the turning point. This is just a plain explanation like you already did in physics. But I will tell you more into details, what will be in the details for the extreme point or turning point, okay? Okay, any question from this physics problem? This is physics, but there are some calculus parts, so I give you this illustration. Hopefully it's related to also your physics, no? Or no? Supposed to learn this, right? This semester, right? Okay, now, have you finished? No? At the break time, do you want to have a break or finish early? Okay. I know. I also want a break. Okay. So, when is your quiz? Thursday, right? Not Tuesday. Thursday. Just to make sure. So maybe Tuesday we can have another exercise. Okay, another exercise. And I will maybe, if I have time tonight or tomorrow, I will record something. Maybe it will be helpful for you. Okay. Now we start from the max minimum value. Okay. Max min value. So we know from the illustration before, we can have some the turning point, right? And it can be lowest point or highest point in our graph. But it's actually not really defining what is our max and min value, because we can have some several perceptions or perspectives. So if we look on this graph here, for example, And we are going to close our interval. So close our interval A and E. So it's not open interval, so we are going to include A and E in the graph. So we are going to observe from x equal A until x equal E. If I say, what is the highest point? The maximum point. Which one? A, B, C, D, E? D, right? D. How about B? Is B maximum? Yeah, we can also say D maximum. But D, we can say D is absolute maximum. For B, we can say it's local maximum. Why local? Because if we are only looking at this part here, that will be our maximum value, right? Or in more general, whenever we see any change between the positive slope and negative slope, there will be some number that is in between. Let's suppose that this number will make the function local maximum. Okay. And if I say, which one is the lowest point, the minimum value? The lowest one is A, right? We can say A is, in this case, in this picture, this is absolute minimum, the absolute minimum. In the closed interval, okay? In the closed interval, this will be our absolute minimum, local minimum, okay? So let me write, just to make sure that we understand. So this will be absolute max. This is local max. This is maybe different color. This is absolute mean. This is local mean. This is local mean. Okay? So we can just design our description on a definition of these two. For absolute maximum or minimum, we are going to observe in all the domain, okay? All the domain. If it is not mentioning any closed interval, it means that we are going to use the general domain of that function. Okay? So use the general domain. But if we are taking the closed interval like this one, from A to E, then that will be our domain, okay? That will be our domain. So we say that the absolute max is B, and local max is B, and absolute minimum is A. And for local max and local min, basically the definition is based on, we are going to take some x and then some constant c that is nearby, which means, for example, we say this B is local max because in nearby this B, for example here and here, it's lower than this local max. Okay? So it should be, and that's why it's called local. It's locally on nearby that x, okay? Local. Okay. And then some theorem, we call this is the extreme value theorem. So for the closed interval like this one, the function, it will attain absolute maximum and absolute minimum. Okay? It must be at some point C and D in a B, if the interval is from A to B, in the closed interval. Okay? So what does that mean? So every functions that can be drawn, like this one, it needs to make its own absolute maximum and minimum. Okay? So this is several cases. So for example, we have this absolute maximum, this is minimum, maximum, minimum, and it can be at the end point. Okay? It can be at the end point because it's closed interval. Okay? And we can have like for example here, C1 and C2, they have the same height, which means both of them are absolute minimum, maximum, okay? Absolute maximum. Okay? So the extreme value theorem for closed interval, you just say that the functions it must be having absolute maximum and absolute minimum. Okay. But how many of them? It depends on the function. It can have 2 absolute maximum or 1 absolute minimum or maybe other variations. Okay, other variations as well. But I think another interesting part, if you have this, just a simple polynomial like quadratic functions, we know that this is having a minimum point right here for the x squared. Okay. So y equals x squared. Okay, so we have minimum right here is minimum. Okay, but if we have, for example, the x cubed, okay, let's say this is our x cubed. Okay. And let's open the interval. Okay, open the interval so we are not observed like in the previous one we have closed interval. So let's open our interval, so we'll be having the domain for all x. We have minimum here, right? And what happened here? What happened here in the x cubed? Do we have maximum, minimum? No, right? No, okay. So this will be giving you no maximum, no minimum, okay? So here, no max, no maximum, no minimum, okay? This is just to show you that in the open interval, the closed interval that we set, the extreme value theorem, is not really working. But if the closed interval, for example, if we take this as an interval, and this is maybe the interval here, then this point here is, those 2 points will be maximum. Okay? But if we look the graph in the whole domain, in the whole x, we cannot see any maximum minimum. Okay? Okay, and then okay, what else? Oh yeah, the Fermat theorem. Okay, Fermat theorem. The Fermat theorem says that if function, if it is having any local max or minimum at C, and if the f prime exists, then f prime is 0. Do not reverse the definition. Okay? So if you take f prime is 0, it doesn't mean that it has local max and minimum. Usually it has, but it not necessarily. Okay? Remember the x cubed before? So if we look the x cubed here, suppose that this is our function. Okay? At the x equals 0, at here, we have the slope that is 0, right? We have f prime 0. But it's not max, not minimum. Okay? So let me write here. This is another phenomenon. So here, f prime at 0 is 0, but f doesn't have max or min value. Okay. And also, interestingly enough, if we look here, we have absolute value of x. I hope you still remember the function. Okay. At x equals 0, you can see that this is the minimum, right? But f prime at 0, what is this? It doesn't exist. The derivative at x equals 0 doesn't exist here. So it's also another phenomenon. Okay, another phenomenon. So here at this function, so f prime at 0 doesn't exist. I hope you still remember how to prove why it doesn't exist. Maybe that will be worthy of your midterm exam. So if f has local max, local min, at those points, the f prime, if it exists, then it should be equal to 0. But if it is equal to 0, it doesn't necessarily to be the local max or min. It can be another term. Like this one, this is not max, not min. We're going to learn about this a few sections later. And here, the f prime doesn't exist, but we know this is minimum. Okay? So these two phenomena need to be taken as important points. So based on this phenomenon, okay, we are going to use another term for this f prime equals 0 or f prime doesn't exist, which we call the critical number. Okay? That's the term. So we're going to write this as a critical number. So a critical number is a number in the domain f such that when we take derivative at that number, c, it will be equal to 0 or the f prime doesn't exist. So these two will be a requirement for the critical number. Okay, for the critical number. So the best way is, if you have a function, then you would like to know like if they are maximum minimum. The best way to write is critical number. So find the critical number, which means finding the first derivative and then solve it with equal to 0. And then there are several ways. First, plug into the line number and check positive, negative, check the slope. If we can prove that it is maybe changed from positive to negative, then it's maximum. If it's changing from negative to positive, it will be minimum. Okay. Let me write that as an example. Okay. And another point is, if f has maximum or minimum at c, then c is a critical number. So I think that is intuitively based on the definition. Okay. Okay, so let's say we are going to have an f of x is x cubed minus 3x squared plus 1. Okay, let's say we have this function. And let's say we want to know like whether it has maximum or minimum. So let's say we have f prime. This is 3x squared minus 6x, right? And then we are going to take the f prime, taking it into 0. Okay. So we are going to have 3x squared minus 6x equal to 0. Or 3x, x minus 2 are 0. So we have x equals 0 and x equals 2. We can take this 0 and 2 into our line number. and check the f prime. Okay, check the f prime. So 0, 2. So check the slope. So this will be the f prime x. So check maybe -1. -1 will be negative, negative, it's positive. And then 1 will be positive, negative will be negative. And then 2, maybe 3 is positive. So it's going to be going up and then down and then up. So we see that this will be the maximum, this will be the minimum. Okay. Okay. So if the question doesn't mention any interval and other conditions, so we just assume on all domain, okay, on that function, the default domain. The default domain. I think some part of this you already learned. Okay, some of you already learned, perhaps, or no? Like finding the extreme point, maximum, minimum, right? Is it turning on? Is that okay? Okay. Okay. Now the next one is the if we have the question like this. Okay. So let me give you more example. So let's say we have function. Is it the same one? Oh, it's the same one. But we have the interval. Okay, we have the interval -1/2. Okay, and then this question is find absolute max and min. So we already know that the critical number, so critical number are x equals 0 and x equals 2, right? Then what we are going to do is we are going to find out each one of them and then also the interval. Okay, so to find, let me write here, to find absolute max and min, need to evaluate critical number and interval or endpoints. Okay. So we are going to check from the interval is -1/2. So we go check on the functions. This will be 1/8. So let me write 1/8 minus or plus 3/4 plus 1, right? Oh, this is minus, sorry. So 7/8 minus 7/8, 7/8. This will be minus 6/8, so 1/8, right? 1/8. And the F4 is 48. 16 plus 1, so 17. And then f0 is 1 and f2 is 4 plus 3, negative 3. So based on what we have here, the f2, this will be the absolute minimum, right? Because that it is the smallest one. And the f4, so x equal 4, this will be the absolute maximum. Okay? So if you are given the interval, you need to also check whether they are also the absolute maximum or minimum. But if it's not mentioning any interval, it means that we are going to use the domain of that function. Oh, they're running. Okay. Okay, any questions about maximum minimum value? Things. Okay. Okay. The next one is we call the mean value theorem. It's actually how we can relate the previous chapter 3 when we learned the linear approximation and the tangent line, and we are going to relate that with this chapter, okay, with this theorem. Okay, now we go to the next one. We start by taking this theorem, which we call the Rolle's theorem. Okay. The Rolle's theorem says that if we have a function, the function is continuous on the closed interval, okay, the closed interval AB, and it's differentiable on the open interval AB. So okay, we are not taking the closed interval. Do you know why? Why we need to take this open? Because at the endpoints, yes, it's not going to continue. So we are just taking to make sure that it's always in the middle. Okay? If, on the endpoints, if you remember when we proved the differentiability, we are not sure what's happened on the endpoint. Whether the slope is going up, going down, we're not sure, right? Because on the endpoint. So we have to make sure that this is going to be open. And then if f of A is equal to f of B, we are going to have some number C in the interval that the f prime will be equal to 0. So this means, okay, this means if we have, for example, if we have, let's say that graph like that. Let's say we have, here is A, and here is B, and let's say the B and A should be the same. So let's say here, so let's say A and B are on the x like that. So f of A is equal f of B, right? This is, so f of A equal f of B. So there will be something in the middle, in between A, B, that is going to be having the slope 0. So let's say this is C. We can try other random functions as you like, okay? And then we need to take the FA equal FB. For example, we have another one. Let's say we have this. Okay. And suppose that maybe here and here. Okay. So this is B, and let's say this is A. So let's say this is equal. Okay. So again, this is FA equal FB. And we also have the slope 0 here, right? And slope 0 here. And we can have more than one. So C1 and then this is C2. Okay. So we say that this 2 makes the slope 0. And then from this Rolle's theorem, that says that if we have AB as interval and then FA, FB equal, we will have number C that will be our critical number, that F prime C will be equal to 0. Okay, now from this Rolle's theorem, we are going to devise or establish a new theorem we call the mean value. Okay, the mean value theorem. Okay, let me just give you first this one. Okay. Two assumptions, the same thing with the Rolle's theorem. We set the f is continuous, f is differentiable on this interval. Okay. But the mean value theorem is giving you the idea that the f prime is equal to fb minus f of a divided by b minus a. Sounds familiar? This is in linear approximation also we are using this. Right? Okay. So this is actually, you can think this like a line equation. Like a line equation. This is the slope. This is the delta y. This is the delta x. Right? So in another forms, we can write this in, so in linear approximation, if we remember, so in linear approximation, we have f prime, let's say f prime a, okay, and this will be approximate by f of x minus f of a, and this is f of a, or a x minus a, sorry. So what's the deal with this? Okay. F prime, we know from our previous cases that the f prime related to the slope of the tangent. Okay. Slope of the tangent. How about this? This is simply just a different point in the curve. We take a line. Okay. We take a line. Or we call this the secant line. Okay. So this is the secant line. So this is secant line, and this is related to the slope, okay, slope of tangent line, right? So suppose that we are going to take that, and yeah, this is the last part before we end the course. So suppose we are taking the graph, okay, And let's say we have maybe a graph like this. Oh. Okay. And let's set up our A and B's here. This is A. Maybe B is here. So we are going to take this line, which is the second line. So this is the second line. So this is B, f of B. This is A, f of A, right? Okay. Now it says that in between of this A, B, see this second line here? There will be another line that is parallel with this. Which means maybe around here that is going to be equal, okay? So we are going to get this. Maybe let me write here, make sure it's equal. Another one will be there. Okay, maybe that is the line. So we could say that this is the number. So the C, or let me write, we can write f of we can write f of B minus f of A equal f prime C B minus A. Or maybe let me just write the original one, okay, easy to understand. So f prime C, f of B minus f of A, B minus A. So there exists number C, okay, whose average rate of change is equal to instantaneous rate of change. I hope you still remember the terms. I'm trying to make it more simplified and practical. So what does these two different forms or structure? We get the idea that when we are having remember the ball, that if we release the ball, it's like it's going down there, and we would like to know like the instant velocity or the instant rate of change, which we are able to see that the instant rate of change is basically the first derivative, which means this one is, we say that it is going to be our instantaneous rate of change. While this, okay, like you see the form, okay? Remember the average velocity from the first part of our course today. So this is the average velocity or average rate of change, which means that we are going to see that there will be some number that these two will be equal. These two will be equal as this graph here. Okay. This is basically this ratio of the triangle, right? This triangle here. Okay. Okay. So if we take this ratio, if you can see, this is actually just a triangle here. In geometric perspective, this is the triangle. So this is FA or fb minus f of a. This will be b minus a. Right? Okay, now let me take some around 10 minutes to finish off, okay? And then we can finish early. Happy, right? Okay, now from this mean value theorem, what is the implications, okay? And I think the textbook doesn't give you more like practical implications so that we can understand what is really the mean value theorem is. So let's go to, let's write the f of b. So let me write what is the implications. So let's start with f of b minus f of a is equal this. Okay, let's start from here. And let's write in terms of f of b equal f of a plus f prime c b minus a. Okay, and let's set up that b is the interval and then c is in between a and b. Okay? So we know that the a for sure a is less than b. Okay, for sure a is less than b. So we could set the definition that b minus a, it should be positive. Okay, let's write again here the same formula. Okay, which means that b minus a is always positive in this case, right? So we are going to see that, let's say this is some value, we can have some value here. So basically what this going to do is we are going to observe that according to our f prime, this will change this value, right? If f prime positive, this will be positive. If f prime is negative, the whole thing here will be negative. Which means that any value here will be plus or minus. Okay, so if we can have several consequences. So if f prime c, if this is positive, which means that the f of b, for sure this will be greater than f of a. Okay, because the f of a plus some value after the f prime. Okay, and if f prime c is less 0, let me make some space here, then perhaps the f of b will get less f of a. And now, because of this, we know that this will be increasing. The f is increasing. Okay. So the f is becoming increased. Okay. And here is getting decreased. And here's the stationary or the extreme point or turning points or extreme point. Or maybe just say stationary, okay? Or say the slope is 0. So we are going to see that when we can somehow determine whether the f increasing or decreasing, we can easily see and observe from the graph. Whenever we find that For example, that one here. This means that, let's say this is positive slope, right? This is positive slope, and then 0, and then negative. We can say that when it's positive, we can say the slope is greater than 0, and the slope here is less than 0. And at this point here, it's equal to 0. Okay? So whenever we find the f prime, and then we find the critical number, and then we can check whether it's positive or negative, then we can pass that critical number, and we can define whether the function will be increased or decreased. This is what we call, I think some textbook call that this is what we call the first derivative test. Okay, I think this will be the end for today's class, okay? Okay, happy?